Okay, fantastic. Okay, yeah, so my name is Matt Hamilton, and I'm in the UK, in Bristol, down in the southwest of the UK. I was a computer science graduate myself about 20 years ago from the University of Bristol. And so, yeah, I studied computer science. I then went and started a web development agency with a friend of mine. We ran that for about 16 years, 15, 16 years, grew to about 15, 16 people. We're mainly building intranets for companies based on an open source content management system called Clone, which is a Python-based content management system. And then from there, I then started working for a US startup based in Los Angeles that were building a health and fitness and nutrition tracking system. And was there for about sort of 3 years. Then unfortunately they ran out of money. And I joined IBM about 2 years ago. And as of yesterday, I'm now what's called a developer advocate at IBM. So for the past 2 years, I've been working in their cloud database division as one of their infrastructure engineers. So keeping all the cloud databases that they offer running. And now I'm basically, it's my job to do talks and go to meetups and conferences and talk to people about the kind of various offerings that IBM have.
Okay, awesome. So how well can you see everyone? I'm trying to
pretty well.
Okay, great. Jalen, you might want to slide over a little bit. There you go.
Yeah.
And can y'all hear okay in the back? Okay,
yeah,
great. So far your interest in AI, that's both part of IBM as well as your own personal interest as well, right?
Yeah, so it started personally. I mean, I've got I've got like a bunch of slides here I was going to go through as well, and you know, some of that. But yeah, I mean, just unofficially to start with yeah, my interest in AI and machine learning was personal. I kind of got into it, and as it happens, IBM do a lot around machine learning and artificial intelligence. People have may have heard of the brand Watson that we have. That powers a lot of like chatbots and assistants, virtual assistants, and things like that. And so I've not had a chance to really do much machine learning and AI from a professional point of view so far, but that's now about to change with my new role as a developer advocate, because it's now my job to kind of pick up some of these AI tools, use them, talk to people about them, feedback, things that come back from developers back to IBM.
Excellent. So did you say you had some slides you wanted to?
Yeah. So I was going to go through, I mean, we'll start, if I get this going, hopefully this should, let's see here. If I share my screen here.
There we go. Ah, perfect. We can see it.
Okay. So you see the slides there?
Yes.
Brilliant. Okay. So this kind of talk that I was doing, this sort of lecture, I've called Ceci and Canard, which is a reference to a Magritte, a famous Magritte painting, Ceci and Pipe. And it's basically it was a joke that started. I'll get into that a little bit. You'll see the reference hopefully soon. But my idea behind this talk is you've already covered, hopefully from what Brian says, a little bit about the theory behind neural networks and a little bit about some of the math behind it and how neural networks, work. So this is really kind of more of a practical sort of demonstration of some of the things you can do, some of the fun stuff I've been doing with neural networks just to kind of test things out and have a bit of a play around. So as I mentioned, I'm a graduate, a computer science graduate from about 20 years ago. I've kind of gone through this, ran a web development agency, worked for a startup, now work at IBM, and I'm now a developer advocate with IBM. So this kind of started with somebody I follow on Twitter kind of shared a meme with me that said, "Draw a duck and share your art." And it started off with a couple of legs and a beak of a duck, and the idea is you fill in the bit in the middle. And there were lots of creative examples of what people had written in there. Some very, very artistic, some not, some a lot of fun, some political, some, all sorts of things. Anyway, I'm rubbish at drawing, I'm rubbish at art, but I thought, well, what if I could get a computer to learn how to draw a duck? Can I train a computer to draw a duck? Can I train it to understand what a duck is? And that was kind of a task, just a fun sort of task I set myself. So what we're using here now, let's see, hopefully you can see that corner there. We're using a type of network I used here called a Generative Adversarial Network, a GAN. So you've covered the basics of a perceptron network or multi-layer perceptron, in which you have a number of layers of neurons. And I think you've worked on the kind of the digit classification example from the MNIST digits example, in which you can try to train a neural network to identify digits in an image, right?
Yes.
And so what this is doing is this is actually a very kind of sort of interesting way of going about generating new data. And the way this works is you actually have two neural networks. You have one called the generator and one called the discriminator. The generator's job is to generate new images that you want to test. So in this example, it's pictures of cats. In my example, it was a picture of a duck. So I've got one neural network that tries to learn to produce images of ducks. And I've got another neural network, the discriminator, that tries to tell the difference between a real duck image and a fake duck image. And you have these two neural networks effectively fight against each other. That's the adversarial bit in the title. So they're trying to outwit each other. One is trying to produce fakes, and the other is trying to tell whether it can produce, tell whether an image is a fake or real. And the idea being is that if the discriminator can't tell the difference between a real image and a fake image, then the generator is doing a very good job at producing fake images, right? So imagine I'm trying to do counterfeit banknotes, and I get a piece of paper and I draw a picture of a president on it or the Queen or whatever, and I give it to you. The chances are you're going to be able to tell that that's a fake banknote because it doesn't look very real. But if I can get very good at producing a fake, you can't tell the difference between the fake and the real banknote. But a qualified like counterfeit detector or whatever would be able to tell the difference. They've learned the subtle little differences between my fake banknote and a real banknote, and they'd be able to tell the difference. So here's where the two networks kind of fight against each other and try and outwit each other. So here we have an example of sort of what's going on here. We have an image of a bank robber here. And what we've done is we've distilled down the basics of that image, the kind of the essence of it. We've imagined we're a sketch artist, a police sketch artist, and you're a witness to a bank robbery, and you have got to describe the person. So they're white, male, 40s, long sleeve black shirt, blue trousers, mask over their eyes, short gray hair. You write down the details, the essence that you think describes that scene that you saw, that image that you saw. And then you take that and you basically go the reverse and you try and build from that a picture. So I take that white male 40s and I generate an image from that. Now, as you can see, the first image I've generated is not that good. You can tell that, I sat down with PowerPoint and sketched this out. And the idea being is that the discriminator is trying to tell the difference between what is real and what is fake. Now, to kind of get into this a little bit more further, we've got to talk a little bit about how it can kind of see what is in an image. And for that, I'm going to cover briefly what are called convolutional neural networks. Now, this might be something that you'll be covering later on in this course, or maybe you know,
Very
further in
soon.
detail?
Yeah, in
Very
a
soon.
couple of weeks. Yes, yes.
Okay, fantastic. So this is very timely then. So a convolutional neural network is a particular type of neural network that's used a lot within image processing in a two-dimensional sense. It's also used in a one-dimensional sense for dealing with things like audio signals, in which you have just a linear time element and some kind of amplitude element. In images, you've got a two-dimensional element. You've got kind of a grid of pixels, and each pixel represents a value in a grayscale image. If you're talking about a color image, red, green, blue, you've actually got a three-dimensional network because you have 3 layers, red, green, and blue. So how does a CNN work? So you take an image, hopefully I've got the right university there, and that is a picture of somewhere nearby you. And you take that image and you apply a filter to it called a kernel. And convolving is just a mathematical term for taking that filter and applying it along the image. So you've got your grid of pixels, and you take this filter, which is just a matrix. So here you can see in the middle, it's just this 3x3 matrix that I've created here. And you multiply your original values by that matrix, and then you take, say, for example, the highest value, and you shift it along and do the same, and you shift it along and shift it along, and you work your way across the image and until you've covered the whole image. And the end result of it is you get something like this, you can see on the right hand side. So this is literally what I've done. I've taken this image here, and I've applied this convolve statement. This is part of SciPy. You might come across, so you've probably come across NumPy, which is a numeric Python library, possibly Pandas, which is for data, for sort of dealing with numbers. There's a library called SciPy, and in there it's got an image class, ndImage, that has a convolve method on it. So you call the convolve method, oh, no, I've gone too far forward, convolve method, and you pass in the image and this kernel, K, and we multiply it, and this is what we come out with at the end. And as you can see, we've kind of detected edges here. And you might recognize this from if you apply various like filters in Photoshop on things, or on your phone. There's various filters you can use in things like Snapchat and that. These are how these filters work. They basically take a matrix and apply it to the image. So we found some edges here. Now, if we apply multiple layers, now you had multiple layers in your perceptron network, multiple hidden layers in your network. If you do this same thing over and over again with a convolutional neural network, then each layer can start to learn a little more detail. Sorry, higher level detail, high level constructs. So the first layer might learn to identify edges. The second layer might learn shapes. So something's a circle, a triangle. The third layer might say, okay, well, 2 circles, are eyes, and the circle around it, that's a face. And then the next layer might say, okay, well, we've got ears and fur, and that's a dog, right? So each layer kind of slowly builds up a higher level understanding of what it's seeing. I mean, when I say understanding, of course, neural networks don't really understand what they're seeing. What they are doing is learning what this kernel, this filter should look like. And they do the same process as what you've done with perceptron, and that you have a back propagation of values. You basically propagate your data through the network. You get you compare it to the desired output. You get a error, and then you back propagate the error through and update the weights in your network. In this case, the weights you have create these filters in the network. So that's how a neural network can see what's kind of going on and start to learn a bit more about an image. So back to our ducks. For our filter here, our generative adversarial network, we needed some examples. We needed it to learn some ducks. So I typed into Google, you know, show us your, or whatever the phrase was, show us your art, here's a duck, show us your art, and got a whole series of ducks. And so I wrote a script to just download them. As you can see, there's some quite creative ones there going on, and asked it to kind of say, okay, given this is what you think a duck looks like, try and produce me a fake duck. Now, the generative network I was using here, the GAN I was using here, was actually one that somebody had written for generating cartoon images. And the test example they used it on were Simpsons characters. And it could generate new Simpsons characters from that. So that's what I thought would be an appropriate thing. And I thought, well, let's see what happens here and feed it through. Now you have these training epochs. Each epoch is one run through the data. And as we start near the top, so one of the early ones, epoch 24, it's just gray. It knows nothing. And as we go on, epoch 100, you start to see a bit of noise going on. Epoch 250, we're starting to get some interesting stuff here. You can see some examples of feet and beaks, a little bit of color coming through there as it starts to learn how to produce an image that looks like the duck images it saw. You might be able to see along the top slightly of some of these images, you start to see text appearing, or what looks like text at this distance. It's not really text, but it knows that it started to learn that in order to produce a decent fake, there was some wording along the top. So we need to put that wording in order to try and fool our discriminator that this is a fake. And then actually what happened when we got to epoch 300, it kind of all blew up. And as you can see, it's gone completely bad again. And what happened was the two networks that are kind of fighting each other, they need to reach an equilibrium. And that didn't happen in this case. So you might remember there's a thing called the learning rate in a neural network. And the learning rate was too high. And what was happening is they were kind of outstepping each other too far, and it kind of all blew up. And if you look at the actual output, so these graphs here, the one on the left-hand side, over the horizontal, the x-axis, you've got the epoch, and we've got the losses from the discriminator and the generator. And as you see, they start to converge. And they kind of reach each other. And at some point around about just after 250, it all kind of blows up and goes unstable. And you can see the generator starts oscillating really badly. So I ran it again, ran it for a bit longer. I lowered the learning rate. You can see in the second chart here on the right, you have a little bit of instability, not as bad as the previous one. And then it starts to stabilize again. And you start to get a sort of a stable point around about sort of epoch 450. It goes a little bit crazy, but it does stabilize a lot more. And what do we get out of it? Well, this is what we see as it evolves. And you can see at certain points in there, this is just looping over. At certain points in there, you see sort of towards the end, you can see, okay, there's some things there that, you know, if you kind of squinted, you might think, okay, that's a duck there. And these are some of the sort of best examples at the end here. Modern art, perhaps. I thought they looked quite cool, actually. You can see it's learned some of the basic features. Again, if you kind of squint, you know, it's easy to see the feet, the color of the feet and the beak, and you can see kind of a little bit about perhaps wings there kind of going on. And that's not such a bad result, actually, considering we had such a varied input. If you remember the input we fed this as to what it constituted a duck, you know, if we go back and look at, well, what constituted a duck, it's quite a wide variety of images. You know, you've got ones here that have cars in them and additional ducks and second ducks and 4 feet ducks and ducks as dragons and ducks doing unmentionable things and all sorts of things here. So, you know, I was quite surprised it came up with that, which was quite interesting. And again, what is interesting here is these images did not exist before. So what we're getting out of this is asking the neural network what it thinks a cartoon duck should look like. You know, these images did not exist before. So this was quite fun. And then, you know, I showed these to some colleagues, and that someone said, "Oh, that'd be interesting." what about if you sort of ran it on faces? And so originally what I was going to do is I grabbed a whole lot of images of my colleagues from the corporate directory, scraped all the images, and I was going to run through to come up with an image of what does a IBM cloud developer look like. And I thought this could actually be quite fun, because if I'm running this on IBM Cloud, I'm effectively asking IBM Cloud what it thinks its creators look like, which I thought was quite a sort of a meta, quite a fun little recursive sort of task there that it could do. In the end, I didn't run it on my colleagues, because I thought there might be some ethical issues there of doing that without asking their permission first before I go feeding their likeliness into neural networks. So I ran it on myself, right? Now, I've got an iPhone, and you might have already sort of found in recent iOS versions that Apple actually have some neural network image recognition stuff built into their phones, into the software, and they are clustering images based upon similarity. And so this is, you might have covered the differences between supervised and unsupervised learning. Well, this is what's called unsupervised learning, and what it's doing is it's trying to find a whole bunch of images that are similar and cluster them together. So all pictures of me, all pictures of my wife, all pictures of my daughter, of my friend, etc., etc. It clusters together because it learns they are similar people. So that was great. If I wanted to train it on a bunch of images of me, I already could get a whole bunch of images. So I could just go into iOS, go to the ones of me that it had already clustered together, select them all, drop them onto my desktop, and run them through a network and see what happens. So the first kind of runs, as you look at this sort of top row here, you can vaguely see maybe there's a person emerging there. Looks a little bit like some sort of horror film in which there's some strange entity coming out of the mist or out of the computer that's going to get you. The second set, okay, they look a little bit more like me. What was interesting was a lot of the images I had sunglasses on. So you could see there's a kind of a constant trend in much of them of dark eyes. And I've got quite dark eyebrows as well, and I think it decided that, okay, a representation of Matt has dark eyes because it had learned from the images. But again, one of the things it had difficulty with was that when I was trying to train it, I was in all different places in the image. So my features were in different locations. They were rotated. They were larger, smaller, different angles, different parts of the image. So it had quite a hard time learning. So to make it easier, I used another sort of intermediate step. And that was using a library called OpenCV. So OpenCV, which stands for Open Computer Vision, is a really fun Python library that has lots of useful stuff in it, quite high-level utilities for doing things like gesture recognition, number plate recognition, digit recognition, that kind of thing that you can do. And it has things like identify facial features. So with a relatively small amount of Python code, I'm not going to go through the exact code here, but there's a face aligner class that can identify where my eyes are, my ears are on an image, and work out what transformation you need to apply to the image to get my eyes into the same place every time. So it will rotate, it will scale, it will skew the image to get a transformation that moves the image to exactly the right place. The next slide has some moving images on it. If anybody is sensitive to moving images, it might be an idea to look away for the moment. But you can see on the left-hand side here, those were the original images. And as you can see, my face moves around a bit. This is just a sample of some of them. There was several hundred from the last, 5 or 6 years I've collected on my phone. You can see on the left-hand side, the original ones. You can see the right-hand side after they've been sort of normalized and transformed. And it's quite eerie because the images have been distorted slightly, but you'll notice my pupils are in exactly the same place in every image, which kind of anchors the rest of my features. So my mouth is in the same place, my ears are roughly in the same place. And that would just make it a little bit easier if I pre-process the images like this first before I pass it into our generative network. So I did that and passed it in, and as you can see, kind of coming out of it, we get some, likenesses that I think, especially if you knew me, you'd say are probably me, especially towards the end of the sort of generations there as it's going through. And again, what is interesting is none of these images exist. These are not filters of existing images. This is a neural network kind of coming back with an answer to the question, give me an image of Matt. And it's what it's learned from my likeness, and it's learned, okay, I've got glasses, my eyes are here, my face looks like this. And from that, it has generated the kind of like the distillation, the essence of what does Matt look like, right? And is then generating there. So in theory, you could leave this on an endless loop and it would produce endless images that were all slightly different as it kind of goes on. So my phone's just picked up for some reason. Anyway, so taking this further, had another play around with as a network called StyleGamma, and there's various examples of this online you can play around with. This one I downloaded and ran within a Jupyter notebook, like an online Python notebook. So on the right-hand side, there's two images that are actual images of me, just taken from my webcam, staring at the computer. On the left-hand side, these two encoded images, they don't exist. They are StyleGamma's interpretation of me. And at quick glance, you think they're real, but then when you look close, you see my eyes are slightly smaller, my beard is slightly smoother, my glasses are slightly different. And so it's not just a filter, there's actually new information in there, slightly different information. And what is quite cool with StyleGamma is you can take those images and it's done several pre-processing steps. So it's already learnt what the basic features are, what eyes are, what ears are, what noses are, etc. And it has also ingested a massive data set of existing images. So there's a public data set called Celeb A that has a whole bunch of pictures of celebrities, and they've been tagged with various features. So male, female, white, black, has glasses, no glasses, smiling, frowning, etc., etc. And it builds up a model that creates this huge, effectively n-dimensional space in which each dimension is a vector along that axis. So there is an axis of smile, and you can traverse through that vector to go from non-smiling to smiling. So here is an example. Now, this is quite freaky. This is going on the left-hand side from -3 on the smile axis to +3 on the smile axis, using an image of myself, and then effectively applying to that what it's learned of what smiling looks like, right? So again, to run again. Yeah, there we go. There's a UK comedian called Alan Carr that I look scarily like towards the end of that animation there. But again, these images don't exist, right? This is its interpretation of what I would look like as you go through. So halfway through that image is kind of like me normally. Oh, stopped it. I've started the next one. So I've given the game away on the next one. The next one is traversing through the gender axis. So it's taken, okay, this is what Matt looks like. Now let's traverse through what we understand of female features to male features and apply them to our understanding of Matt and produce an image. And so again, what we get is this weird thing where in the middle, it's me. And you go from, at the start, you go from a very female version of what it thinks I look like to a very male version. As you see, my hair disappears. How do I get that running again? Come on. There we go. My hair starts to disappear completely. Beard gets even bigger, features more rugged. And yeah, it's quite spooky to watch. It's sort of interpretation. Now, there's a live instance in which you can do this live and move around with the various axes, and you can actually lock particular axes and move along other axes once you've locked one. So, for example, if you go all the way to male, all the way to facial hair and get a big beard on it, lock the facial hair, and then try to move the gender axis back towards female, you get this weird point halfway through where the image shears. The neural network has no idea what a female with a beard looks like because there's none in its data set. And it gets it sort of breaks halfway through. And then it starts to kind of learn, and you get at the end a woman with very long hair draped across her face. Because what it thinks is, okay, this is how we get a female with facial hair. And you see this image with a female with long hair kind of going like across, obscuring half her face, as that's what it learns it should look like. So let's move on to another machine learning technique, a thing called reinforcement learning. That's my dog, Violet. If you've got a dog, or a pet or a child, you will possibly have gone through this process. Give them a command, reward them from some behavior, go back to step one and keep going round. It's how we learn, right? As human beings, it's how we learn. We try something. If it works well, we get a reward. Now that might be a personal reward, or it might be a reward given to us. And we learn to associate that reward with the behavior, and we learn what should happen. Now, formalized in a machine learning sense, you have an environment, you have an agent that acts upon that environment via an action, and the environment comes back with a state and a reward. So what does that look like in a more concrete sense? So if we were looking at learning to play a video game, so the old Atari Breakout game, in which you've got a paddle moving along the bottom, and you've got to move the paddle so that it hits the ball hits the paddle, and you bounce it back up and try and break the blocks. So the state space in this case is a grid of pixels, say 128 by 128 pixels. The action space is two actions. We can move left and we can move right. And the reward is the game score. So we want to maximize the score that we get. And what happens is it tries to play over and over again to maximize reward. Now, initially, it has no idea what it's doing, and it just moves randomly. And eventually, it will get the paddle in the right place to hit the ball, to hit the brick. And when it hits a brick, the brick disappears and it gets a point. And it goes, that's a good thing to do. And it learns over time, over maybe 1 million, 10 million iterations of the game, how to play the game. Now, again, it has no idea as what it's actually doing. It doesn't really understand what a ball or a bat or a block is. All it is doing is learning, okay, this is the sequence of actions I need to do to get a reward. So what's quite great is it's a fairly generic algorithm that can be applied to any problem that you can formulate in this way, in which you have some state, you have an action, and you have a reward. So it can be any type of game. What else could we apply it to? Well, we could apply it to things like financial prediction. So I'm interested in algorithmic trading and cryptocurrencies. I'm not presenting this from my yacht yet, so there's a way to go yet. I'm not rich from this yet. But let's say we had a state space that includes things like, what are open trades? What does the financial data look like at the moment? Say, looking at the average price movement. Is the price trending up? Is it trending down? There's a whole number of technical indicators that financial traders use that are all sort of derivatives of the price in various ways. And we have an action space, so buy, sell, and hold, and a reward, which might be something as simple as profit. And so what we want to do is train a reinforcement learning algorithm to learn when to buy and sell and hold stocks or currencies or cryptocurrencies or whatever it's trying to trade. And effectively, we teach this as a game for it to learn. And the idea being is we want it to do well and be profitable. And this chart here is a number of runs of the algorithm, and what we've run up to 450,000 iterations. And in the sort of background, you can see kind of like faded out the raw values, and then in the foreground is the kind of average values. And as you can see, it's kind of trending up. So it's learning slowly how to be profitable. Now, like I said, I'm not presenting this from a yacht yet, so there's no sort of silver bullet. In fact, with a lot of financial data, you're trying to actually predict a fairly chaotic system of which there's no straight answer that can be derived through simple machine learning of things like the price. So people include other things like sentiment analysis, what's being said on the news, what's being said on Twitter, what's happening around the world. Do different things correlate? What are we looking at in terms of volatility? And trying to build up all of these models and then use machine learning, the same neural networks that you're learning about, to try and predict what happens here. But rather than just try to predict the price with, like you might do with a supervised learning algorithm. So with a supervised learning algorithm, you could say, okay, here's a bunch of inputs, here's a bunch of outputs. Try to learn what input maps to what output. And that way you could kind of say, okay, if the price data looks like this, we expect the price movement to go up or down or stay the same. Now, that's called supervised learning because you've kind of got the answers there and you're using the raw data and trying to learn what the answers should be. With reinforcement learning, you don't have the data there, you don't have the rules. All you have is the reward. So going back to our example of this game here, it has no idea what the rules of Breakout are. It doesn't need to know the rules. All it does is it learns what sequence of actions give me the highest score. And there's some fantastic examples online of some really hilarious things where machine learning algorithms have learned totally ridiculous moves, but that have maximized the score. So there's a driving game in which one of the AI that is learning how to play the game has learned that if it just spins the car around and round and round as it goes around the track continuously, that because of the way the scoring works, it can hit certain number of items much easier, and that's how it learns to play. Right, so a completely unrealistic sort of driving scenario, but that it has learned, okay, these are this is still a valid rule, this is still a valid move. I can sit there and spin the car around and around and around in place, but I can hit certain points as I go along. So financial prediction, we talked a little bit about. One of the things with sort of tying these two things together, look at convolutional neural networks. So convolutional neural networks are often used to categorize things. So is this a cat? Is it a dog? Is it an apple? Is it a banana? Well, what if you take your raw data and format it to look like an image? So each one of these 8 examples is financial data taken from, again, a cryptocurrency exchange, a Bitcoin exchange, I think it was, or XRP exchange, in which you have a number of buyers, which are the green area at the top, and a number of sellers, the red area at the bottom. And it shows how many people are willing to buy and sell and at what price level. And each one of those 8 squares is a series of time moving along the x-axis. So over time, you can see the price moves up and down, and the difference between the buyers and the sellers will expand and contract. And the little blue marks you might see in are where actual trades took place. So at what point did the buyer and the seller's price kind of meet enough that a trade took place and was agreed? And the idea is that can we take these images and feed them into a neural network and say, okay, well, this was the last 120 seconds. What happened in the next 10 seconds? Did the price go up or down or stay the same? And you can take these and then pass them into an image recognition service. So at IBM, we've got a service called What's an Image Classifier. And I could take a whole bunch of these images, put them in a zip file. These are all the images in which I knew the price then went up. These are all the images in which I know the price then went down. These are the images in which the price stayed roughly the same. Upload those 3 zip files to Watson image classifier and say, okay, learn those images. And then if I give you a new image, tell me whether you think it's going to go up, down, or stay the same. And again, you know, you could get better than 50-50 odds on it. So if you're trying to guess whether it could go up or down, you could get about 55% accuracy. And you could say in most cases, well, as long as you're above 50%, then on average, you're going to be winning. Unfortunately, in the real world, there's then inefficiencies and costs that come into it. Every trade you make, there's a fee to be paid, and that eats into it. So you need to be better than just 51%. You need to be probably close to sort of 58-60% before this would become reliably profitable. But it was an interesting experiment. And it was a case of taking data that is not really an image and formatting it to look like an image, such you could then use image processing algorithms on it and see whether they could learn from these. Can they spot patterns? Can they learn what a price jump would look like, what the imminent things before a price jump would look like? So there's a number of toolkits. I think you folk are using Keras, I believe, for learning. There's a number of different ones. All the ones on the left there are Python, so scikit-learn, Keras, TensorFlow, kind of starting higher level and going sort of lower level as you kind of go down. On the right are some other interesting ones that are used for things like mobile development. So Swift, which is a programming language used for iOS development. They're working on Swift for TensorFlow. CoreML is Apple's machine learning for on-device image recognition. TensorFlow Lite for Android. They've ported TensorFlow for Android as well. So it's not just on the on desktops and servers, but actually happening on devices as well. Things going on. And as I mentioned, IBM have got a number of tools for kind of automating some of this stuff. So you're learning the theory and how these things work. IBM have got a number of tools. So Watson machine learning, you can upload a bunch of stuff, a bunch of data. Watson Auto AI can actually tune the algorithm. So how many layers in my neural network should I have? How many neurons should I have at each layer? What loss function should I use? What optimizer should I use? What learning rate? And it will try different ones and work out what works best. And the idea behind that is to go from raw data to predictions very, very quickly in a sort of a business sense. And Watson Studio, which allows you to run sort of Python stuff through the web against a hosted cloud instance somewhere. So you don't need to have a graphics processor locally. You can go and run it off on a big cluster of graphics processors somewhere else. So yeah, that's the talk there. Hopefully that was interesting, and talking about some of the sort of practical aspects and some of the fun bits there.
Yeah, that was amazing. Actually, let's give me my hand. Yeah, that was awesome. I have a few questions. I'm gonna see if anybody else has some questions too, but just so I don't forget, I will definitely email you the recording of this. And y'all, I'll probably post an assignment that has the recording. Have y'all discuss some stuff about it too. But y'all have questions? Okay, go for it, Jay.
As far as like core ML for like Apple's development toolkit, do you have any I guess like any kind of tips on like using that actual like API as far as like trying to like identify buildings instead of like images or whatever, like pictures, images, or whatever?
Okay, so I think it was a little hard to hear that, but it was, do I have any tips for using Apple's Core ML API for image recognition?
For identifying images, yes. For
identifying images. Well, so Core ML gives you a API in which to access these machine learning models, but you also need a model that has been pre-trained on images. And there's a number of existing models you can download. So there's a number of kind of competitions for generating like the best model, and there's a number of like pre-trained models. So Google have one called VGG16. There's one called ResNet. There's a number of different ones, and each year somebody comes out with a better one. There's one called Inception. Comes up with a better model and then trains it. And the training is what takes a long time. Now, you're used to what you've seen so far in multi-layer perceptrons with like 2-3 layers. Some of these big deep neural networks have blocks. Like Inception has something like 16 blocks, and each block is about 3 or 4 different layers that are repeated over and over again. And these things take huge amounts of memory and processing time. But what you can do is you can actually, so with one of the tools we've got at IBM allows you to train a model using, our CPU power and export a core ML model from that you can drop into Xcode, into a Swift app, and then actually do the recognition from there. And I'm actually going to be doing hopefully a talk on that soon at a local meetup. But probably the example I'll be doing is again, taking a couple of zip files of classified images. So I want to recognize the difference between a bottle of beer and a bottle of cider or something. I can take pictures of the cans of beer and the cans of cider and upload those to what's an image recognizer and get it to learn the difference between the two, and then export that trained model down back and just drop it into Xcode, into a simple app. And then within that app, you would basically say, take a photo with a camera, take that photo, pass it into the Core ML API against this pre-trained model. And out of that, I should get a probability. So it's 95% that it's beer and 5% that it's cider or whatever, and then can do what I want from there. So hopefully that helps a bit.
Yeah. Just so I don't forget, that's actually sort of related to Jalen's senior project. Obviously you're not going to fly to the UK for the local meetup, but when is that? Is there any way that he could somehow, because sounds like that would be an awesome talk for him to see. Well, obviously,
yeah,
really, but.
That's there's no date for it set yet. But I will definitely ping you when it's ready. My contact details are up on the slide now, and Brian will send them around if anybody has any questions. But beyond this, by all means, contact me, and I'll be putting some of this stuff up online. So either soon, my role now as a developer advocate is to kind of do these presentations and talks and do these kind of things and show people how to use these APIs. So if I don't do it at a talk within the next few months, I will definitely do it separately and do an worked example.
Other questions from Matt?
Yeah, I had one. So I know can you hear me right now?
Yeah, just about, yeah.
Okay, cool. I know earlier when you were talking about how that network had made its like entirely new picture. It was the picture that looked like you, but it wasn't. How's it creating like that picture? Does it have like a 3D modeling software, or like is it just drawing it, or what?
So what it is doing is, so the question was, how is with the GAN, the Generative Adversarial Network, how is it actually generating the output image? So the output image is just a grid of pixels, the same as what the input was. So the input was an array of pixels. So say those images were quite small. I think they were like 64 by 64 pixels or 128 by 128 pixels. So it was being input a grid, a NumPy array of those pixels. And when it outputs the same thing as well. And that then just gets converted to an image from the pixel values. So the values run from, say, well, in the case of the output from here, they go from 0 to 1. And you scale that up from, say, 0 to 255 to represent the values, grayscale values of an image. And if you do that on 3 layers, you have the red, green, and blue. And that gives you the kind of the color that comes out of it. So it's generating, the output is a grid of pixels. Everything that neural networks do is basically an array of values, a matrix comes out.
So that final layer then has however many pixels. That's how many neurons it has at that final layer.
Exactly. So if you remember from your MNIST, the digits example, I think your final layer had 10 output neurons.
Right.
Because that represented the probability from each of the, the values you were expecting. You wanted to get from 0 to 9. So you had 10 output neurons. And so with the case of a GAN, you have as many output neurons as you have pixels that come out of it. So, you'd have, say, 64 by 64, whatever that is in total, neurons on the output.
Gotcha.
And then the adversarial part of that, the second one, does it only have the 2 output neurons?
Yeah, so it has 2 output neurons that give the probability of real or fake.
Right, okay.
But as an input, it has the full grid of pixels because it takes the image in.
Right.
The generator starts off with an image takes as its input random white noise. And so it just takes in white noise, just random values. And then from there, it learns, okay, what do we need to do to turn that into an image that looks like a picture of me? And the discriminator just basically takes the output from the generator and just has 2 neurons, to represent real or fake.
Other questions? One of the ones that I had was some of the sample size, the training data sizes. Like take for example the one of just you, the one that you trained to generate images of you, and you pulled those from your iPhone because it automatically clusters together. How many images did that end up being?
A few hundred, like 300 maybe, something like that. How many images are on there for the past 6 years or something? I think it's like about 300. That sort of order of magnitude. Yeah.
That's interesting to me because the MNIST digit data set has 50,000 images. So it's interesting to me that it could do as good as it did with just a few hundred. That's what I was imagining. It was maybe just a few hundred or something. But that's
I mean, the step that I did of normalizing the images, in which I got, it used OpenCV to get the eyes in the same place, and so the rest of the features would be roughly in the same place. That certainly helped it learning. Now, generally, in most neural network instances, you actually don't want that because you get a problem called overfitting. And overfitting is where your neural network learns to exact a very specific thing. So in your example of kind of like cats and dogs, like it only recognizes a cat if a cat is sat in the middle of the picture looking at the camera. It doesn't recognize a cat that's lying down. It doesn't recognize a cat that's upside down. It doesn't recognize a white cat because it's been trained on black cats, et cetera, et cetera. It doesn't recognize a Rottweiler versus a poodle, on the dogs, because it's learned too specifically. So generally you want as much information as possible, and you actually want it to be a bit varied because that stops you getting the overfitting. Now in the thing that I was playing around with, I wanted it to produce an image of me. So I did, overfitting wasn't a problem there. If I wanted it to produce a general image of what a regular, just, any old person looks like, then you'd want to give it as much data as possible in different variations, different orientations. You would want that because you want it to be able to identify this is a person, whether they are, sort of this way to the camera, straight to the camera, upside down. You want it to learn that the essence of a person is a face with eyes and nose, not a person that happens to have this exact value at this pixel.
Right. Gotcha. Okay. Excellent. Other questions from that? Okay. Well, thank you again so much. And like I said, I'll email you or I'll probably Dropbox or something, since it'll probably be a big video. Awesome. Thank you again.
Yeah. And thanks very much.
All right. We'll talk to you later then.
Great. Thanks. Bye.
Bye. Oh, end meeting. There we go.